Hello everybody, and in this video we're going to be talking about generating functions. Generating functions are extremely useful in counting problems and probability problems, which are basically the same thing as counting problems because you count in probability. But anyways, you can use generating functions for counting problems, and you can use them to represent geometric series and other types of series and sequences, such as the Fibonacci sequence. So overall, generating functions are actually very useful for counting and sequences, I'd say. So first, we're going to start with a counting problem that may seem pretty familiar. It's just a simple division problem, dividing, let's say, 10 coins among 3 people. So here's our first problem. We want to divide 10 coins among 3 people. How many ways can we do this? So at first you may not understand this, but the generating function for the first person is 1 plus x squared plus x cubed, and so on. The generating function for the second person is the same thing, and the generating function for the third person is the same thing. So here's the part where I will kind of explain this. And so think of this, the coefficient of x to the 0th power, which is 1, as the number of ways to choose 0 coins, for the first person to choose 0 coins. The coefficient of this x is the number of ways for this first person to choose 1 coin, which is 1. And this is the number of ways for the coefficient of x squared is the number of ways for this person to choose 2 coins, and so on. And as you can see, the coefficient of each of these terms is all 1, so we just have 1 plus x squared plus x cubed, and so on. And you will get why we have it like this later on. So let's see what happens when we multiply these all together. So we cube this because there are 3 people and they all have the same generating function. But before we try computing that, we're going to try computing something simpler. 1 plus x squared squared. And we're going to do this by using the distributive property. So we have our 1 right here, and we're going to multiply it by each of these terms. And that would give us 1 plus x squared plus x cubed, and so on. Now we're going to take our x term right here, and we're using the distributive property, of course. So we're multiplying by each of these again. And we have x plus x squared plus x cubed, and so on. Oh, I guess we're just going to have to deal with that. Just going to erase these lines, and we're going to start the distributive property with the x squared right here, and we're going to distribute again. And you might be seeing where this is going. And we have x squared plus x cubed, and so on. And this is x cubed, and so on. So if you see that if we keep going and we add these all together, this becomes 1 plus 2x plus 3x squared plus 4x cubed plus 5x, and so on. Now we can try computing this and multiplying this whole thing by 1 plus x squared plus x cubed, and so on. And you can see this is getting rather big. So we have to compute this. Well, let's try doing this by using the distributive property again. So we have 1 plus 1 x plus x squared plus x cubed, and so on. And then when we multiply by the 2x, we have 2x plus 2x squared plus 2x cubed, and so on. 3x, we can keep going, 3x squared plus 3x cubed, and so on. And for the 4x, we just have 4x cubed, and so on. And if we keep continuing like this, we can kind of notice something here. We see that the first term is 1, and then the coefficient of the second term is 1 plus 2. The coefficient of the third term is 1 plus 2 plus 3. The coefficient of the third term is 1 plus 2 plus 3 plus 4. And we know how to calculate sums of consecutive numbers, which there's a formula for it, which is n times n plus 1 over over 2, which is also equivalent to n choose 2. So we have 1 plus 2 choose 1 x plus 2 choose 2 x plus 3 choose 2. Actually, I think I messed up, sorry. So we start with 2 choose 2 plus 3 choose 2 x, this is right, plus 4 choose 2 x squared, and so on. And as you can see before, if we saw what we have before this one, we see that that's actually equal to 1 choose 1 x. 1 choose 1, sorry. I'm making a lot of mistakes here. 2 choose 1 x plus 3 choose 1 x squared, and so on. So we can see a pattern here with what's happening with each time we multiply by 1 plus x squared plus x cubed. And as it turns out, 1 plus x squared plus x cubed to the fourth power is 3 choose 2. Why am I making so many mistakes? 3 choose 3 plus 4 choose 3, and so on. So with this, we've actually found a pretty cool pattern. But what does this have to do with our problem where we want to divide 10 coins among 3 people? So, as it turns out, the coefficient of x to the 10 of this big, whatever this is right here, is actually our answer. So, if we go back to this thing right here, which is 1 plus x squared plus x cubed to the third power, and we want to find the coefficient of x to the 10th power here, then we have 12 choose 2, which is equal to 12 times 11 over 2, which is 66. So our answer is actually 66. There are 66 ways to divide 10 coins among 3 people. And why is this? Well, if we actually look back at whenever we're distributing and multiplying, and we can see that x to the 10, there are many ways to make x to the 10. One of them includes 1 times x to the 9th. There's also x squared times x cubed times x to the 4th. And as you can see, all of these things are actually inside each of these small parts that we were multiplying together. And when they add up, they're all equal to x to the 10, and they're all different ways to make x to the 10. So, in reality, we're kind of just doing a counting problem, but just doing algebra. And the reason why this is useful, even though we're doing so much multiplying with these infinite polynomials, the reason why these are actually useful is because, first of all, we find a neat pattern like we saw before with these combinatorics. And you can figure out, for example, if you wanted to split 9 coins among 3 people, and we could also figure that out. So, overall, this is actually a really cool approach to counting problems, and I hope you enjoyed this video.